In this lecture, we're going to discuss ionic interactions and lattice energy of these crystals in more detail. So as a summation from our last video, we have this ionic bond. Now, it's not really a bond in that the electrons aren't being shared like they are with a covalent bond, but it is really an electrostatic interaction between a positively charged cation and a negatively charged anion. Metals easily lose electrons because they have a low ionization energy. Non-metals readily gain electrons because they have a large electron affinity. And so what happens is the electron leaves the metal and ends up in the valence shell of the nonmetal. So now you have a positively charged cation and a negatively charged anion, which according to the rules of Coulomb's law are attracted to each other. So it is this attraction that holds together this lattice. So as an example, let's look at potassium chloride. So we look at what group potassium is in. It's a group 1, so it has 1 electron. And we look at chloride and we see that it's in group 7 and it has 7 electrons. The idea using the Lewis theory of ionic bonds is that this electron leaves potassium, so potassium is ionized, and that electron is accepted by the chloride, or chlorine, to form chloride. So potassium is starting out with an electron configuration close to argon, but it has 1 electron in its 4s1 level. Chlorine has 7 electrons in its valence shell, and its core is neon. Once argon loses that 4s electron, its electron configuration matches that of argon. Once chlorine gains that electron to become chloride, it now has the electron configuration of argon. So neon plus 3s2, 3p6 is the argon configuration. Both of these ions are now in a noble gas configuration and have achieved the octet rule. Now notice this says noble gas configuration, not turned into a noble gas. This is still chlorine. It's still got the same number of protons in the nucleus. We have not changed the identity of these, but what we have done is made this ion more stable by changing the electrons that this nucleus has access to, giving it the stable configuration of a noble gas. So let's practice predicting the Lewis structure of potassium sulfide. So we find potassium on our periodic table and see that it's in group 1, so it's going to have 1 valence electron. We look over here and we see that sulfur is in group 16 or 6A or 6, and that would tell us that it's going to have 6 valence electrons. So we sketch out our potassium ions with their single valence electron and our sulfur with 6. And what happens is the sulfur takes 1 electron from each of the potassiums. So now we have 2 K pluses and a S2 minus. So when these come together, they form this electrically neutral, in theory, electrically neutral compound. So this will form that lattice structure with that smear of electron cloud around it, like we saw in the last video. So the formation of an ionic compound is usually exothermic, or it releases energy. So if we were to take this sodium and this chloride and combine it and measure the amount of energy that's released when this compound forms, we would measure out negative 411 kilojoules per mole. That is a lot of energy. So for every mole of sodium chloride formed, 411 kilojoules is released into the surroundings. This delta H sub F stands for delta H of formation, or enthalpy of formation. It literally means the heat released when forming, or the heat absorbed when forming. If this process were endothermic, this sign here would be positive. So where does this energy come from? We see that the ionization energy of sodium is plus 496. The electron affinity of chlorine is negative 349. So this energy does not come from the ionization energy of sodium. It costs energy to rip an electron away from sodium. Some energy is released upon chlorine taking that electron to become chloride, but it's not enough to get to here, because if you added these together, you would not get that number. The answer for where this energy comes from is called the lattice energy, which is the energy associated with forming the whole crystalline lattice of the alternating ions and the subsequent sharing of those, of that like electron cloud around that lattice. So how do we measure this experimentally? Imagine this experiment where you have gaseous sodium ions and gaseous chloride ions, and those are allowed to come together and form a lattice, a crystal lattice, and there's an amount of heat released, and that is measured. So in this experiment, they found that a certain amount of energy was released, and that is the lattice energy. So the lattice energy is the amount of heat released when these compounds, when the ions come together to form that crystal lattice. And where that energy comes from is the potential energy decrease that's noted by Coulomb's law for the strong attraction between these oppositely charged particles. So let's look at these trends in lattice energy. So we see that lithium, sodium, potassium, cesium, as you go down this group, you see the lattice energy getting closer to zero. So why might this be? Well, if we look at the trend in size, we see that lithium is the smallest, cesium is the largest. So two smaller compounds are able to be closer to each other. And remember, with Coulomb's law, they have to be that right distance apart to have that attraction. So since lithium is smaller, it's able to be closer to chloride. It has a smaller distance. And so that causes this higher lattice energy than cesium, which is much larger. And so these two, they have a greater distance. And so the lattice energy is closer to zero. Now there's still quite a bit of energy in here. It's negative 657 kilojoules per mole, but it is less negative than this one. So when you're looking at negative numbers, it's the closer to zero, the less favorable it is. Or the more negative it is, the more favorable it is, okay? So most favorable, least favorable. Still favorable overall, but less so than the three above it. Okay, so to summarize, the cation size, as it goes up, the distance between the two charges increases, which is what decreases the lattice energy. So let's look at another trend here. Sodium fluoride has a lattice energy of negative 910. Calcium oxide has a lattice energy of negative 3414. Wow. What's going on here? It's not size, because these are pretty similar in size. Okay, 231 picometers versus 239. So what is it? Well, it's the magnitude of charge. So again, remember our Coulomb's law. As the magnitude of charge increases, the energy increases. So higher magnitude, greater force of attraction, means greater lattice energy. So more favorable, more exothermic, meaning that for every mole of calcium oxide formed, almost over 3,400 kilojoules are released into the system or the surroundings around the reaction. So this cool thing about Lewis theory is we can actually make predictions based on it. Remember, theories allow us to make predictions about behavior. And Lewis theory helps us predict that ionic compounds would have high melting points. So why is this? Well, in a solid, ions are all fixed in place. They have all the charges interacting with each other. If you heat this up and you make a liquid, now what happens is these ions can all move around. So they can still interact with each other, but they have a lot more space and a lot more fluidity. And so this tightly packed, ordered, charged structure is being disrupted. So remember that picture we saw in the first series of these lectures showed the cations with the electrons all the way around, just kind of smeared around. So we have these oppositely charged oppositely charged particles interacting with each other, and we have to break apart all of those interactions, and that requires a lot of energy. So we have high melting points due to the energy required to break the crystal lattice. So let's predict which would have a higher melting point, sodium chloride or magnesium oxide. Well, we know that we have a higher lattice energy for magnesium oxide because it has +2 and -2 charges versus the +1 and -1 charge. And if the lattice energy is higher, then we would predict that the melting point would be higher for magnesium oxide. So as the ion attraction gets stronger, it's harder to pull the ions apart, and you'll have a higher melting point. And this is in fact what we see. The melting point for sodium chloride is 801, and for magnesium oxide, it's 2852. Another property of these ionic compounds is they conduct electricity when in solution, but not in a solid state. So when they're in a solid state, we've got our positively charged sodium in purple and the green chloride in green here, and the electrons are being held by our chlorines and not held by our sodiums. But when these dissolve in water, we now have a whole bunch of free negative anions and free positive cations, which allow electrons to flow freely through the solution. So these allow the electrons to move in between these charged rods. These ions cannot move between the charged rods when they're held in that crystal. But when it's separated and surrounded by water, then these ions can move, and that is how the electrons can travel between the two rods. So here's our summary. When we're drawing Lewis symbols, metals are always going to donate the electrons to the nonmetals. Ionic compounds, we classify them by their lattice energy. The more exothermic the heat of formation, so the more negative, the closer together the ions are held. Higher magnitudes of charge give you a higher lattice energy. Smaller ion sizes give you a higher lattice energy. And a higher lattice energy equals a higher melting point. And these ionic compounds will conduct electricity in solutions, but not in a solid state.